So welcome to part 3 of lecture 30. So here's the example that I'm going to work out today. And let's first take a look at the example. And it may seem like you've wandered into the wrong class because it doesn't look like a linear algebra problem to begin with, right? And so what the example that we're going to do is show that there's a polynomial qx, and that we're looking at degree 1 or less polynomials, such that when I integrate, I forgot my integrating factor. When I integrate px times qx from 1 to 0, it's the same thing as integrating px times sine pi x 1 to 0 dx for all polynomials. Okay, so let's think about what this is saying. It literally looks like a calculus problem, right? Because it's saying on this side, I want to integrate this. And so I have this trig function. And I'm integrating, saying that for any polynomial I put here, there's another polynomial out there that I can, instead of evaluating this integral, I could evaluate the integral on the left-hand side. Right? So this seems kind of, both, to me, kind of amazing that we can kind of somehow replace the trig with a polynomial, as long as we're kind of restricting, what we're evaluating on. So this is great. Let's say you had to do a whole bunch of these integrations involving trig functions, and you may not be happy about doing that because if you sit down and write a couple of them, you know that you're going to have to get your tables out or get Wolfram alpha out. On the other side, you just have polynomials, and those are very easy to integrate, so you don't actually have to do much work. Now, this again, as I said, this looks like a linear algebra calculus problem. What does it have to do with linear algebra? Well, I picked this because it kind of really shows you the power of the Riesz representation. Okay, and to use the Riesz representation, okay, we have to show that first of all we can apply it. Okay, so we want to take the point of view that we're actually working with inner products. Okay, so P1, the set of all polynomials, degree 1 or less, right? We know it's a vector space, and in fact, it's an inner product space. And this is the inner product. So I take a pair, P and Q, of polynomials, and I send it to the number that I get by integrating P times Q and then evaluating it from 0 to 1. So looking at that definite integral. Okay, so this is an inner product space. And then the map here that takes the polynomial p and sends it to this number is a linear functional. Okay, so because it's a linear map. So we go back to the hypotheses of the Riesz representation theorem. We have a vector space that's a finite dimensional inner product space, and we have a linear functional. Okay, so these two things here imply that the hypotheses of the Riesz representation theorem are met. Okay, so that part is good. And so let me just kind of write out then what we can conclude. All right, so the Riesz representation theorem now implies that there exists some q, I don't need q1, I just qx in the set of polynomials of degree 1 or less, such that this integral, so integrating px times sine pi x dx, which is my linear functional, is equal to some inner product px qx, right, which is equal to 0, 1 px qx dx. Okay, so right here, this, or maybe I'll point it right here, this equal sign exists by the Riesz representation theorem. This equal sign exists. And notice that now on the outsides, this is actually what we wanted to prove, right? We wanted to prove that there is a polynomial that satisfies these two things. So the way that we're going to do it is we notice that, hey, this is a linear functional. The Riesz representation theorem says that I can find some different polynomial q to write it as an inner product, and then I'm expressing it in terms of the inner product. So we know that there are things exist. That's what the Riesz representation theorem says. But now, how do we find that qx? Okay, well, that's great because now we can use our procedure. We first find a normal orthonormal basis for our space, then we compute these values, and then we return them. So in the rest of this part, I'll show you how to compute the orthonormal basis. Okay, so I'll just put down here, we use the procedure to find the missing polynomial qx. Okay, so the first step of the procedure is to find an orthonormal basis for the set of polynomials in degree 1 or less. And how do you do this? Okay, well, you start with any basis. You start with any basis and you hit it up with the Gram-Schmidt, because the Gram-Schmidt procedure takes any basis and turns it into an orthonormal basis. So the first stage of the orthonormal, the Gram-Schmidt, is pretty straightforward. Oh, so let me just get some notation here, right? So we can follow the notation in the Gram-Schmidt section. So our original basis is V1 is 1 and V2 is x. So the first step is very easy. Our first element of our orthonormal basis is E1 over V1 times the norm of V1. And you can do a little calculations and just see that this number down here is just 1. Okay, so the first element is just 1. Okay, and now we need their second element, so we just need one more guy. And according to the formula, this is V2 minus V2 and the inner product E1 times E1 divided by the norm of V2 minus V2 E1 times E1. Okay, so there's two things we need to find. We need to find the vector at the top, and we need to find the vector at the bottom, or the value at the bottom. So there's some calculations. So here are the calculations that I need. Well, first of all, I need this inner product, V2 and E1. So V2 is x, E1 is 1 from above. And so we have to integrate from 0 to 1 of x dx. And you can probably do this in your head. This is x squared over 2 from 1 to 0. So that gives me 1/2. So this tells me what this term is, and it tells me what this term is. And now what we have is, so V2 minus the inner product of V2 and E1, E1 is equal to x minus 1/2 times 1. So we can just write that as x minus 1/2. Now we need to figure out the length of this vector. Okay, so we're finding the length, or not the norm of this vector. So remember that is the square root of the inner product of x minus 1/2 with itself. And let's do that calculation. Hopefully I have enough space here. So this is equal to integrating from 0 to 1, x minus 1/2 squared dx, square root. We'll expand out what's happening underneath the square root sign. So this gives me x squared minus x plus 1/4 dx. Carrying on, so this underneath gives me x cubed over 3 minus x squared over 2 plus 1/4 x from 1 to 0, and I'm taking the square root of all that. And at the end of the day, this, if you follow out all the steps, this gives me 1 over the square root of 12. Okay, so my second basis element is E2 was equal to x minus 1 over 2 over 1 over the square root of 12. So I can write that cleanly as the square root of 12 times x minus 1 over x minus 1 half. Okay, so our orthonormal basis. Our orthonormal basis of P1R is E1 is 1 and E2 is equal to the square root of 12 times x minus 1 over 2. So when we come back, we're going to use this orthonormal basis to kind of finish up the problem.